Hello everyone, welcome back. So in this video, we are going to explore handwritten digit classification. So rather than trying to figure out whether somebody survived the Titanic or didn't survive the Titanic, what we're going to do is we're going to have a data set of different images. And what we're going to try to, each of these images is going to have a handwritten digit, and we're going to try to have a machine learning algorithm that can look at an image of a 3 and say this is an image of a 3, not an image of a 6. And this is part of a very general problem in computer vision where you might show the computer a picture of a cat, and it needs to be able to identify that it's a cat, not a dog. And this is incredibly important for a variety of things. Some cool applications of this include automatic caption generation for images. If you have a searchable feature on your iPhone where you can type in, find me a photo of boats, and then it just pulls up a bunch of photos of boats, somewhere under the hood is machine learning that's automatically identifying this is a picture of a boat, that's a picture of a boat, that's not a picture of a boat. Also, driverless cars. Without getting into it, driverless cars require computers to look at an image and identify what it is. Computer vision, it's generally awesome, and it's one of the biggest areas of machine learning. So today we're going to focus on the task of handwritten digits. And okay, we could motivate this by going to the post office or something, which I think is what we wrote down. And that is important. But really, in my personal opinion, the reason why I really like handwritten digits is that this was kind of a benchmark data set for the machine learning community for a very long time. And after we got really good at developing handwritten digits through the development of something called a convolutional neural network, then success on other data sets quickly followed. This also does come with a dark side because the technology for recognizing handwritten digits is also what's used in, for example, facial recognition. But in any case, it's a very powerful technology. So let's get started by importing our standard imports. And now we're going to load in some data. And the most famous data set is something called the MNIST data set. But today, for learning purposes, we're going to work on a pre-designed data set that comes with sklearn. So we're going to say from sklearn data sets, we're going to import a function called load digits. And then we're going to call this function and say digits is equal to load digits, called with no arguments. So we've got a new variable. Let's see what it is. Type of digits. Okay, it's a bunch. Okay, that's not really very informative, but I do happen to know that a bunch happens to be a little bit like a dictionary. So we can do digits.keys. And we see there's a bunch of different keys. And the two we're going to care about are data and target. So data is going to be our predictor variables, and target is going to be our target variable. Now I claim that our predictor variables are going to be images. So let's take a look at what these look like. So if we look at digits, data.shape, we see that it's 1,797 by 64. So what this is going to mean is it's going to be 1,797 images. Each image is a 64 by 1 vector. And it's a 64 by 1 vector because it's actually an 8 by 8 grid that was reshaped. So let's take a look at this. Let's first look at image 0. So let's go with I equals 0. Pick is equal to digits, data, I. Pick is equal to pick.reshape, 8 by 8. Looks like I forgot the E. One of these days I will learn how to type. And we'll do fig x equals plt dot subplots x dot imshow pick. And to make it look nice, I'm going to use cmap color map is equal to plt.cm.binary. Okay, so it's an 8x8 image, very pixelated for lack of a better word, because there's only 64 pixels. Very blurry and grained, but you can see this is a 0. And now this is the first entry. If we look at entry number 200, instead we would get a 4. And the same thing for all of the other 1,800 points in the data set, approximately 1,800. That's what our data looks like. Now let's see what the target looks like. All right, we go with digits target dot shape. 1,979 by 1. Okay, that makes sense because there's one answer for each of the 1,797 images. So this looks pretty complicated, but we actually can analyze it using a lot of the same tools we've been using for everything else. This is just another classification problem. It's just with a different type of data. So we could say from sklearn.model selection, import train test split. And now we're going to say xtrain, xtest, ytrain, ytest is going to be equal to train test split digits.data digits.target. And I need to put an E in selection. All right. And now we're going to say from sklearn dot linear model import logistic regression. And from sklearn dot model selection import cross-val score. We're going to create a model. M is equal to logistic regression. I'm going to set some parameters. Random state equals to 0, so you get the same result as me. And I'm also going to set the solver to be equal to liblinear. Cross-val score. So now we can call a cross-val score. We're going to apply our model to xtrain and ytrain. And let's use tenfold cross-validation and take the average. And Mike made a typo, and let's go this logistic regression. It's icky. Okay, we see we got 96% accuracy. That's actually a little bit better than I was expecting. You can see I pre-wrote that about 95%, but there is some randomness. So, here's something to point out. We do this whole random state equals 0 thing to make it always get the same result as me. But that only works if you type exactly what I type. So if you want to make sure to get 96.4333, make sure to make exactly the same typo as I did. In any case, we get about 95, 96%. So that's pretty good. And this was with a simple model. We're basically using the same stuff as before. So a nice thing about images is we're gonna create a confusion matrix. And the confusion matrix is going to help us understand the mistakes. And then we're gonna look at the mistakes and we're gonna be able to understand the mistakes. You're gonna see that there's 8, which the network thinks is a 9. And you're gonna see they really do kind of look like 9s, or they're kind of funny looking. In any case, we're gonna get into that. So first we need to do is we need to create a confusion matrix where we say m dot fit xtrain ytrain. So we're going to train on the whole data set, and we're going to say ytrain pred for our prediction is going to be m dot predict x train. And we can take a look at y train pred. And we see we get a bunch of numbers, so that makes sense. These are the predictions of our model. Now we say from sklearn.metrics, import confusion matrix. C equals confusion matrix. And we're going to look for the differences between y train and y train pred. And okay, so we get a matrix where most of the entries are on the diagonal. Most of the non-zero big entries are on the diagonal. And so diagonal entries are good. That means we got it right. And since we had 96% accuracy, it's not surprising that we got all the big numbers on the diagonal. Now, if you look at this 2 down here, this is a confusion between an 8 and a 9. It's in row 9, column 8. And so since it's in row 9, this means the model predicted a 9, but in fact, the digit was an 8. And like I said, 8s and 9s, they sometimes look kind of the same sometimes. But now let's try to look at this a little bit more in depth. And so let's make a mask. And the mask is going to be our mistake. So this is going to be wherever y train is not equal to y pred. Y train pred, sorry. Mistakes is going to be equal to x train mask. Mistake labels is equal to y train mask. And then mistake preds will be equal to y train pred mask. And then let's take a look. There's our mistake predictions. And here are the mistake true labels. Okay. So we could see it confused an 8 and a 1, an 8 and a 9, a 3 and an 8. And now let's plot each of these things. And this is a bit tricky, but let's do this slowly. So let's go with m plots is going to be the number of plots we're going to make. And this will be the length of mistakes. And now let's make a plot. Fig x is equal to plt dot subplots. We're going to have one row, and the number of plots should be the number of the mistakes. And this should need to be kind of big. So we're going to say fig size with a z, is equal to 20, 4. So now we're going to have a plot for each of our mistakes. And now we say for I in range m plots. So now we're going to loop over. We're going to say xi dot mshow mistakes I. But mistakes I is a 64 by 1 vector, so we need to reshape it into an 8 by 8. And we also want it to look the way that we want it to look, so we'll do cmap is equal to plt.cm.binary. Okay, so yeah, I think now we understand why our model made mistakes. I mean, I'm looking at this nonsense and I can't tell what the heck it is. But maybe it'll be a little bit easier if we know the answer. So let's label our x's. So we go with an xi dot set title equal predicted stra mistake preds I plus true plus stra mistake labels. And hopefully my parentheses are matched. All right. So apparently this is a 1, and it predicted an 8. I honestly don't know how that's a 1. Somebody has bad handwriting. I think that is an 8. I'm going to go with our model is right, and whoever wrote this has shitty handwriting. And here it predicted an 8, but it's actually a 9. And you can kind of see how maybe that looks like an 8 where the bottom loop was a little bit funny. So our model is pretty darn good. So based off of cross-validation, we think that our model is going to get about 95% accuracy. And we also have this visual inspection that means we think it's pretty darn good. So now let's do with an m.score score on the test set. And okay, we got 94% accuracy. Like I said, we thought that it was going to get around 95% accuracy. And so this is well reasonable. When I ran this earlier, I actually got 96% accuracy on the test set, but randomness. So now the next question is can we do even better? And yeah, this was, we just used a logistic regression, and there's lots of sophisticated techniques for, a lot of sophisticated techniques which have been developed really in the last 10 years for image recognition. So one of them is neural networks, and there's many very sophisticated neural networks, but the most primitive type of neural network is what's called the multi-layered perceptron. And this uses a multi-layered structure of linear transformations stacked on top of each other to extract features of the data. Now, you don't have to worry about that. What you need to know, or what I'm going to show you, is that you can import it from the neural network MPL classifier package. You do NN is equal to MLP classifier with some other parameters. And then other than that, you then fit it exactly the same way as all of these other models. And then we go ahead and look at our score. Okay, 96%. So that was a little bit better than what we got before. Now let's try another method. Let's try something called random forests. This is like a decision tree, but you use lots of different decision trees, and you then apply like 10 different randomly generated decision trees, and say 6 of those trees think it's a 5 and 4 of them think it's a 2, then majority wins. This is decision trees plus randomness plus democracy. Okay, so we go with a random forest classifier, and now let's score this bad boy. Okay, and we see we get even better. We say we get 96.2%. All right, that's slightly different than what I got when I ran it before writing the notes. We don't need to dwell too much on the exact numbers. All right, and this is where we're going to stop. But if you want to stick around for a few more minutes, I also have some bonus material. This lecture hits right up against my research interests. I don't have too much. I've just got this, but 1 or 2 more minutes of some bonus material and some other useful tricks. So another thing you can do before putting your data into a model is to transform it, to pre-process your data to get new data, which has the same labels, but maybe is hopefully easier to classify. And so one tool that was developed in 2012 by Stefan Millat, and I've been working on developing updated versions of it the past several years, is something called a scattering transform. And this actually works in a way which is really similar to the convolutional neural networks I mentioned at the beginning of the video, which the convolutional neural networks are basically the key to the success of everything cool that's been done with classifying images in the past 10 years. This is like a mathematical model for theoretical understanding and blah, 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 blah. But without getting into a bunch of advanced math, it's a way of pre-processing your data to make it so that you can then do image classification using a simple linear classifier. So if you want to run this is kind of an advanced topic, and it doesn't come with Anaconda standard. So here's another useful trick in its own right. You need to pull up Anaconda prop, and then you type in pip install Kematio. Let me make sure I'm spelling Kematio right. All right, looks like I am. And then you press enter. And nothing happens because I already have this installed. This is a requirement already satisfied. If you do this, there might be some kind of worry noises. And then from Kematio.sklearn, I'm going to import the two-dimensional scattering transform. We're dealing with images which are two-dimensional. Similar things work for classifying audio or video or stuff. And then I'm going to initialize a scattering transformer. And so then what I'm going to do is I'm going to take this, if I take the scattering transformer of the data, of the training data, what I get is something which is going to be 347, it's going to be 1347 by 81 by 2 by 2. Or this might actually not work. Oh, no, it does. So I've got to reshape this data into something that's dealing with images. And then I'm going to rerun the linear regression on this reshaped data. Ah, that's what it is. Yeah, it needs to be reshaped into 81 times 2 times 2, because that's what the shape is. Okay. Hold on. Misspoke briefly. Okay. So what you have to do is when you call the transformer, you need to reshape the data into 8 by 8 grids. Then the output of the data is actually a 4-dimensional NumPy array where it's going to be 1,347, which that's the number of points in the training set. It's 80% of the data. And then it's an 81 by 2 by 2. So then we have to turn this back into a matrix. So we do 1347 by 81 by 2 by 2. But this is just a whole training of the data. And now what we can do is we can compare the cross-val score we get with exactly the same model. It's just the same basic logistic regression on the transform data versus the original data. And this is going to take a couple of seconds. Okay, we see that on the transform data, we're able to get 97.4%, but on the non-transformed data, you're able to get 96.4%. So in addition to showing you just some stuff I've been working on, there's two kind of takeaways from this. Is one, sometimes you can pre-process your data in an intelligent way to improve the performance of simple linear classifiers. And two, sometimes you need packages which aren't native to Anaconda. So you pull up Anaconda prompt and type in pip install. This was bonus material. So thank you for listening. I'll see you again next time.